In this video we're going to look at the kind of manipulations we do to systems of linear equations when we're solving them and the effect on the corresponding augmented matrices. Let's begin with an example of solving a linear system. We have some equations here: 3x plus 4y is equal to 6, x plus 2y is equal to 5. If you're going to solve these, you probably begin by eliminating the x from equation 1 by subtracting 3 times equation 2 from equation 1. So let me label these so we know what we're talking about. Here's equation 1 and here's equation 2. After we've done that, we can read off the correct value of y from the new equation 1, simply by multiplying the first row by minus a half. Finally, we can finish up by eliminating the y from the second equation by subtracting 2 times the first equation from the second. That will leave us with y is equal to 9 halves and x is equal to minus 4. We've solved these equations. So what did we do when we were solving these equations? Well, we had certain manipulations which we did, which were sometimes we multiplied a particular equation by a non-zero number, and sometimes we subtracted a multiple of one equation from another. Finally, if you wanted to, you could also swap the order of the equations without changing anything. So those are 3 types of manipulations you can do to any linear system. The corresponding effect on the augmented matrices of these linear systems is called a row operation. A row operation is one of the following 3 things that we can do to a matrix. First, you can add lambda times row I to row j. Here, j should be not equal to I, but lambda can be any number you like. There's a special piece of notation for these row operations. This row operation is written like this: row j goes to row j plus lambda times row I. Next, you could multiply row I by lambda, where lambda is a non-zero number. If you're not going to change the solutions of your system of linear equations, you need to make sure you don't multiply by 0, since that would make one of the equations disappear. This row operation is notated like this: row I goes to lambda times row I. And finally, you can swap rows I and j, and the notation for this is row I and then a 2-headed arrow and then row j. Let's go back to our previous example and look at the corresponding row operations to the manipulations we did. We begin with this system of linear equations, whose augmented matrix is 3, 4, 6, 1, 2, 5. As I said before, some people like to put dots here in their augmented matrices. I'm not going to do that. It's fine if you want to. The first thing we did in our manipulation was to subtract 3 times row 1 from row 2. Sorry, that's the wrong way around. We subtracted 3 times row 2 from row 1. So the row operation is row 1 goes to row 1 minus 3 times row 2. If you do that row operation to our augmented matrix, you'll get the augmented matrix of the new system, which is 0, minus 2, minus 9, 1, 2, 5. The next thing that we did was to multiply the first equation by a non-zero number. The corresponding operation on our augmented matrices is to multiply row 1 by minus a half. So here row 1 should go to minus 1 half row 1. That's the notation for this row operation, and the result is 0, 1, 9 halves, 1, 2, 5. The next thing we did to the equations was to subtract 2 times the first equation from the second. The corresponding row operation is that row 2 goes to row 2 minus 2 R1. This time the augmented matrix becomes 0, 1, 9 halves, minus 4, 1, 0, minus 4. That's better. So let's tidy that up a bit. Okay, and finally, if we wanted our variables to appear in the opposite order, so we wanted x on the first row and y on the second row, then we could use the final type of row operation, which was to swap two rows. So just for the sake of using it, let's do that. Swapping R1 and R2, which was notated like this with a two-headed arrow, leads us to 1, 0, minus 4, 0, 1, 9 over 2. And there the corresponding equations simply give us the solution. They say x equals minus 4 and y equals 9 halves. Here's an important observation about row operations. Row operations are invertible. What that means is, for each row operation R, there is another row operation S, such that doing S then doing R, or doing R then doing S, gets you back to where you started. In other words, the composition of those two row operations is the same as doing nothing. That's easy to see just by thinking about the row operations one type at a time. The first type added lambda times row I to row j, and of course you can get back to where you started by subtracting lambda times row I to row j. The next type multiplied row I by a non-zero scalar lambda, and you can get back to where you started by multiplying by 1 over that scalar. Finally, if you swap rows Ri and Rj, then you can get back to where you started by swapping rows Ri and Rj again.